This is how all too many computers from industrial countries are recycled, if you can call it that. Poor people in India and China cook circuit boards by hand for the parts. But it doesn't have to be this way. The technology exists to mine e-waste, recovering the material, using it again, and doing away with what has become an awful downside to today's modern electronic marvels. Old electronics, or e-waste, is the fastest growing segment of waste today. Despite international treaties, about 80% of the e-waste from the United States and United Kingdom is going to risky recycling programs in Africa, India, and China. The European Union is clamping down on e-waste by making producers take back products once they're no longer useful, with a program called WE. They have demanded the virtual elimination of 6 certain hazardous substances in electronics, a program called ROS. They're expected to demand a detailed analysis of the environmental impact of all electrical devices, a program called EUP. They are also expected to implement a detailed accounting of all chemicals used in electronics sold in Europe, a program called REACH. But why do these devices have dangerous material in them in the first place? The answer starts with the most basic item in electronics, the solder that has connected components since the days of the vacuum tube.
Take it up to high temperature, the material melts, you cool it down, and then you don't think about it anymore. And there are billions and billions of these solder joints made, essentially without thinking about every year.
Solder is a combination of tin and lead. Lead is an element that can harm the health of people, especially children. Most countries have removed it from products like paint and gasoline. Through the ROS directive, the European Union ordered the removal of lead along with mercury, cadmium, hexavalent chromium, and 3 types of brominated flame retardants. Lead is also in every cathode ray style TV set and computer monitor. Mercury is found in flat panel screens that are used with computers, in laptops, cell phones, and flat panel TVs. Some batteries and circuit boards contain cadmium, which can cause cancer. Brominated fire retardants, which are toxic to the nervous system, are sometimes used in the plastic housing. A 2001 EPA report estimates that in America's landfills, 70% of the heavy metals and 40% of the lead come from electronics. Even more metals are on the way.
What we have experienced over the last decades is a tremendous increase in the demand of metals on the one side, but also in the variety of types of metals which are used. Today, more than 60 different metals, for example, are used in electronics.
The attempt to rid our electronics of lead has had its problems. Monitors were exempt from ROS because there is no substitute. As for solder, lead tin is giving way to a silver-copper tin combination, but it's more likely to break than the old solder. This is a big issue for high-vibration applications such as automobiles.
It gets even worse when you're starting to think about, all right, what happens in an airplane? What happens in military systems? And the other thing that has gotten an exemption so far from the European Union in changing to lead-free are medical devices. The alternatives all require mining that is much more environmentally degrading. For example, tin, silver, copper is the material that we've been using. Silver is very difficult to mine. Cyanide is usually used in the mining of silver.
Nevertheless, companies are making progress.
IBM has eliminated most of the substances already. So our product stewardship program has covered, for example, PBB, PBDEs, brominated flame retardants since the early 80s.
This means thinking about the entire product.
This is removal of those 6 materials throughout the product. It's not just in soldering, it is in cabling and all the elements where the substance may occur. So you may go as far as getting a so-called lead-free solder, but then forget you've got lead in the paint.
But there's no universal approval of those substitute materials.
Greenpeace finds it difficult to endorse the substitutes, partly because, and usually because, there is just so little information about the substitute, about the safer, so-called safer alternative.
But the European Union plans additional regulations. REACH stands for Registration, Evaluation, and Authorization of Chemicals, and demands a full accounting of chemicals used in electronics.
If it is in, it should be documented somehow, and if it is in, it should be traceable and trackable along the supply chain.
That means producers need to know not only what's in the components they make, but in the components they buy. One company is creating software that warns designers when they're about to use a component with a hazardous substance.
It's a phenomenal way to, in the schematic design, be able to pop up a note that says this part that you're about to design with only has a life expectancy of 6 months. So it's a great way to keep the engineers on the leading edge.
But databases and computer warnings are not enough. The push is to get companies and their engineers to think differently.
I think first thing which should happen is that the companies take it very seriously and have it as an integral part of their policy on developing new products. So this should be something what is basically a common thinking, not something extra on the top of the process.
So they have the recycling process in their mind, of course. They know the knowledge of the recycling process very well, and then they design their own products based on this knowledge.
And it's not just companies that need to think about changing. Schools have to incorporate these new life cycle design concepts into their engineering programs.
We actually collaborated with several universities to start a new engineering course. It's not an usual engineering, but it's engineering for environment kind of thing.
But engineering programs are already very rigorous, and adding an entirely new layer of thought regarding life cycle analysis won't be easy.
Well, life cycle analysis and life cycle training is really not widely taught in engineering. In most places, undergraduate engineers, for example, might get 1 or 2 lectures on life cycle analysis in 4 years.
Everyone has too much on their plate. Everyone has too many courses they try to put in a curriculum. Everybody has a difficult time finding an evening to do a little bit of extra study. But I think it's an important thing that we need to do in order to get industry to operate at a high level as it interacts with the environment.
Ultimately, it will be up to the engineers and their own ethics.
I've been in a number of technical meetings where junior people, when they raised concerns about privacy or about the ethical implications of some new technology, were essentially told, that's not, your job to think about. You're an engineer, you're hired to build it, you're not to think about that. And I think it's a lot better if actually those kinds of discussions are allowed to occur.
The fundamental definition of engineering is design. That engineers prototypically do designs of all sorts. And that it's in the design process and thinking about design that they are challenged ethically.
I've seen some products, even in our company, that were very much changed in the early stages by examining ethical issues.
In the future, it won't be enough for an electronic device to do the job it was designed to do, or doing it better than a competing product. With the number and variety of electronic devices growing rapidly, those devices will have to do their job using fewer resources. And they'll have to do so during manufacture, during use, and be built in such a way that they'll be less likely to end up as dangerous waste and a hazard to health. For the next generation of engineers, solving this problem while still creating devices that can do more, do it more cheaply, and enthrall the next generation of consumers will be a challenge that will have a significant impact on our world for years to come.